Here's another example. We have a 5 kilogram force, a 5 kilogram mass with a force that's a function of time, and we're given the force at 3 different values of the clock time t. At t equals 0, the force is 0. At t equals 0.02 seconds, the force has increased to 300 newtons, and at 0.05 seconds, the force is back to 0. So we have this force that is applied over a 0.05 second interval. Just before the halfway point, the force is 300 newtons. The force starts at 0, ends at 0.05 seconds, at 0 again. And that the force is linear between these two times and linear between these two times. Now, the forces usually aren't linear in time. They tend to be more like sine functions or exponential functions, Gaussians actually. But for the moment, we're going to make the approximation that these forces are linear. So the force has a graph. Well, let's look at the graph. The force goes from 0 to 300 newtons in 0.02 seconds, and then by the 0.05 second time it's back to 0 again. So we have this sharp spike of force. And we want to determine the impulse. Well, impulse is the product of average force and time interval. What is the average force in this case? The force function is linear from 0 to 0.02 seconds, and then linear again from 0.02 to 0.05 seconds. Let's look at 0.02 to 0.05 seconds. We see that the average force here, since the force is a linear function, the average force will just be the average of the initial and final forces, 300 newtons and 0. And we average those two by adding them and dividing by 2. We find that the average force is 150 newtons. We'll similarly be able to determine that over the first interval the average force is 150 newtons, so that when we multiply the average force by delta t, we'll be multiplying 150 newtons, which is our average force over both intervals, by the entire 0.05 second time interval, and getting an impulse of 7.5 newton seconds, which is 7.5 kilogram meters per second. We'll note that the 7.5 kilogram meters per second is equal to the area under this curve between the x-axis and the graph of the force. That area is equal to the average altitude of this triangle, which is half of the 300 newton maximum altitude, 150 newtons, multiplied by the 0.05 second base or width of the triangle, and we get 7.5 newton seconds, which is our impulse. Now, to find the change in velocity, which probably wasn't stated, that's been our goal here though. Our m delta v is the impulse, so delta v is impulse divided by m, the mass, and we divide the 7.5 kilogram meter per second impulse by the 5 kilograms to get our 1.5 second meter per second, our 1.5 meter per second change in velocity.